A solar cell is an electrical device that converts the energy of light directly into electricity by the photovoltaic effect. It is a form of photoelectric cell, defined as a device whose electrical characteristics are for example current, voltage, or resistance vary when exposed to light. Cells can be described as photovoltaic even when the light source is not necessarily sunlight. Photovoltaic cells are used as a photodetector, detecting light or other electromagnetic radiation near the visible range, or measuring light intensity. The operation of a photovoltaic cell requires three basic attributes: the absorption of light, generating either electron-hole pairs or excitons; the separation of charge carriers of opposite types; the separate extraction of those carriers to an external circuit. In contrast, a solar thermal collector supplies heat by absorbing sunlight, for the purpose of either direct heating or indirect electrical power generation from heat. A photoelectrolytic cell, on the other hand, refers either to a type of photovoltaic cell, or to a device that splits water directly into hydrogen and oxygen using only solar illumination. Building block of a solar panel. Assemblies of photovoltaic cells are used to make solar modules which generate electrical power from sunlight. Multiple cells in an integrated group, all oriented in one plane, constitute a solar photovoltaic panel or solar photovoltaic module, as distinguished from a solar thermal module, or solar hot water panel. The electrical energy generated from solar modules, colloquially referred to as solar power, is an example of solar energy. A group of connected solar modules is called an array. History. The photovoltaic effect was first experimentally demonstrated by French physicist Edmond Becquerel. In 1839, at age 19, he built the world's first photovoltaic cell in his father's laboratory. Willoughby Smith first described the effect of light on selenium during the passage of an electric current in a February 20, 1873 issue of Nature. In 1883 Charles Fritz built the first solid-state photovoltaic cell by coating the semiconductor selenium with a thin layer of gold to form the junctions. The device was only around 1% efficient. In 1888 Russian physicist Alexander Stoletov built the first cell based on the outer photoelectric effect discovered by Heinrich Hertz in 1887. Albert Einstein explained the underlying mechanism of light-instigated carrier excitation the photoelectric effect in 1905, for which he received the Nobel Prize in Physics in 1921. Russell patented the modern junction semiconductor solar cell in 1946, discovered while working on the series of advances that would lead to the transistor. The first practical photovoltaic cell was publicly demonstrated on April 25, 1954 at Bell Laboratories. The inventors were Darrell Chapin, Calvin Southard Fuller and Gerald Pearson. Solar cells gained prominence when they were proposed as an addition to the 1958 Vanguard I satellite. By adding cells to the outside of the body, the mission time could be extended with no major changes to the spacecraft or its power systems. In 1959 the United States launched Explorer 6, featuring large wing-shaped solar arrays, which became a common feature in satellites. These arrays consisted of 9600 Hoffman solar cells. Improvements were gradual over the next 2 decades. The only significant use was in space applications where they offered the best power-to-weight ratio. However, this success was also the reason that costs remained high, because space users were willing to pay for the best possible cells, leaving no reason to invest in lower-cost, less efficient solutions. The price was determined largely by the semiconductor industry. Their move to integrated circuits in the 1960s led to the availability of larger boules at lower relative prices. As their price fell, the price of the resulting cells did as well. These effects lowered 1971 cell costs to some $100 per watt. Berman's price reductions. In the late 1969, Elliot Berman was investigating organic solar cells, when he joined a team at Exxon SPC who were looking for projects 30 years in the future. The group had concluded that electrical power would be much more expensive by 2000, and felt that this increase in price would make alternative energy sources more attractive, finding solar the most interesting. He conducted a market study and concluded that a price per watt of about $20 per watt would create significant demand. The first improvement was the realization that the standard semiconductor manufacturing process was not ideal. The team eliminated the steps of polishing the wafers and coating them with an anti-reflective layer, relying on the rough sawn wafer surface. The team also replaced the expensive materials and hand wiring used in space applications with a printed circuit board on the back, acrylic plastic on the front, and silicone glue between the two, potting the cells. Solar cells could be made using cast-off material from the electronics market. The company started buying up reject silicon at very low cost. They used the largest wafers available, thereby reducing the amount of wiring for a given panel area and packaged them into panels. By 1973 SPC was producing panels at $10 per watt and selling them at $20 per watt, an 80% decrease in 2 years. Navigation market. SPC convinced Idland Signal to use its panels to power navigational buoys. After finding that automatic power, the market leader had purchased and shelved a solar navigation aid prototype from Hoffman Electronics to protect its battery business. Tideland's solar-powered buoy quickly overtook automatic. The rapidly increasing number of offshore oil platforms and loading facilities led ARCO to buy Solar Power International, forming ARCO Solar. ARCO Solar's factory in Camarillo, California was the first dedicated to building solar panels, and was in continual operation from its purchase by ARCO in 1977 until 2011 when it was closed by Solar World. Following the 1973 oil crisis, oil companies used their higher profits to start solar farms, and were for decades the largest producers. Exxon, ARCO, Shell, Amoco and Mobil all had major solar divisions during the 1970s and 1980s. Technology companies also participated, including General Electric, Motorola, IBM, Tyco and RCA. Declining costs. Further improvements reduced production costs to under $1 a watt, with wholesale costs well under $2. Balance of system costs were then higher than the panels. Large commercial arrays could be built, as of 2010, at below $3.40 a watt, fully commissioned. As the semiconductor industry moved to ever larger boules, older equipment became inexpensive. Cell sizes grew as equipment became available on the surplus market. ARCO Solar's original panels used cells 2 to 4 inches in diameter. Panels in the 1990s and early 2000s generally used 125 ohm wafers. Since 2008 almost all new panels use 150 ohm cells. The widespread introduction of flat-screen televisions in the late 1990s and early 2000s led to the wide availability of large, high-quality glass sheets to cover the panels. During the 1990s, polysilicon cells became increasingly popular. These cells offer less efficiency than their monosilicon counterparts, but they are grown in large vats that reduce cost. By the mid-2000s, poly was dominant in the low-cost panel market, but more recently the mono returned to widespread use. Manufacturers of wafer-based cells responded to high silicon prices in 2004–2008 with rapid reductions in silicon consumption. In 2008, according to Jeff Powatmans, director of IMEC's Organic and Solar Department, current cells use 8–9 grams of silicon per watt of power generation, with wafer thicknesses in the neighborhood of 0.200 ohm. First Solar was briefly the largest panel manufacturer in 2009, using a thin-film CDTE cell sandwiched between two layers of glass. Silicon panels returned to dominance via lower prices, partly from the shift to Chinese manufacturers. By late 2011, a drop in European demand due to budgetary turmoil dropped prices for crystalline solar modules to about $1.09 per watt, down sharply from 2010. Prices continued to fall in 2012, reaching 62 cents per watt by 4Q 2012. Applications. Solar cells are often encapsulated as a module. Photovoltaic modules often have a sheet of glass on the sun-facing side, allowing light to pass while protecting the semiconductor wafers. Solar cells are usually connected in series in modules, creating an additive voltage. Connecting cells in parallel yields a higher current. However, problems such as shadow effects can shut down the weaker parallel string, causing substantial power loss and possible damage because of the reverse bias applied to the shadowed cells by their illuminated partners. Strings of series cells are usually handled independently and not connected in parallel, though individual power boxes are often supplied for each module, and are connected in parallel. Although modules can be interconnected to create an array with a desired peak DC voltage and loading current capacity, using independent MPPTs is preferable. Otherwise, shunt diodes can reduce shadowing power loss in arrays with series parallel connected cells. Theory. The solar cell works in several steps. Photons in sunlight hit the solar panel and are absorbed by semiconducting materials, such as silicon. Electrons are excited from their current molecular atomic orbital. Once excited, an electron can either dissipate the energy as heat and return to its orbital or travel through the cell until it reaches an electrode. Current flows through the material to cancel the potential, and this electricity is captured. An array of solar cells converts solar energy into a usable amount of direct current electricity. An inverter can convert the power to alternating current. Efficiency. Solar cell efficiency may be broken down into reflectance efficiency, thermodynamic efficiency, charge carrier separation efficiency, and conductive efficiency. The overall efficiency is the product of these individual metrics. A solar cell has a voltage-dependent efficiency curve, temperature coefficients, and allowable shadow angles. Due to the difficulty in measuring these parameters directly, other parameters are substituted: thermodynamic efficiency, quantum efficiency, integrated quantum efficiency, VOC ratio, and fill factor. Reflectance losses are a portion of quantum efficiency under external quantum efficiency. Recombination losses make up another portion of quantum efficiency, VOC ratio, and fill factor. Resistive losses are predominantly categorized under fill factor, but also make up minor portions of quantum efficiency, VOC ratio. The fill factor is the ratio of the actual maximum obtainable power to the product of the open circuit voltage and short circuit current. This is a key parameter in evaluating performance. In 2009, typical commercial solar cells had a fill factor greater than 0.70. Grade B cells were usually between 0.4 to 0.7. Cells with a high fill factor have a low equivalent series resistance and a high equivalent shunt resistance, so less of the current produced by the cell is dissipated in internal losses. Single pi-N junction crystalline silicon devices are now approaching the theoretical limiting power efficiency of 33.7%, noted as the Shockley-Queisser limit in 1961. In the extreme, with an infinite number of layers, the corresponding limit is 86% using concentrated sunlight. In September 2013, a solar cell achieved a new record with 44.7% efficiency, as demonstrated by the German Fraunhofer Institute for Solar Energy Systems. Upconversion, one efficiency technique, is to incorporate lanthanide-doped materials, taking advantage of their luminescence to convert infrared radiation to visible light. This process, called Upconversion, occurs when two low-energy infrared photons are absorbed by rare earth ions to generate an absorbable photon. As example, the energy transfer Upconversion process consists in successive transfer processes between excited ions in the near-infrared. The Upconverter material could be placed below the solar cell to absorb the infrared light that passes through the silicon. Useful ions are most commonly found in the trivalent state. O+ ions have been the most used. O3+ ions absorb solar radiation around 1.54 AA micrometer. Two O3+ ions that have absorbed this radiation can interact with each other through an Upconversion process. The excited ion emits light above the C-band gap that is absorbed by the solar cell and creates an additional electron-hole pair that can generate current. However, the increased efficiency was small. In addition, fluorindate glasses have low phonon energy and have been proposed as suitable matrix doped with O3+ ions. Cost. Solar power costs consist of three categories: Manufacturing, distribution, installation and subsidies. The cost before subsidies is stated per unit of peak electrical power. Manufacturing, distribution, many costs are proportional to the panel area or land area involved. A higher efficiency cell may reduce the required space and so reduce the total plant cost, even if individual cells are more costly. To be useful in evaluating solar costs, they must be evaluated under realistic conditions. Installation. Consumer installation costs have reduced only slowly, because of its reliance on human labor. Concentrated solar power offers greater economies of scale, given its much larger size. Subsidies. Solar-specific feed-in tariffs vary by country and within countries. Such tariffs encourage the development of solar power projects. Grid parity. Widespread grid parity, the point at which photovoltaic electricity is equal to or cheaper than grid power without subsidies, likely requires advances on all three fronts. Proponents of solar hope to achieve grid parity first in areas with abundant sun and high electricity costs such as in California and Japan. In 2007 BP claimed grid parity for Hawaii and other islands that otherwise use diesel fuel to produce electricity. George W. Bush set 2015 as the date for grid parity in the U.S. The Photovoltaic Association reported in 2012 that Australia had reached grid parity. The price of solar panels fell steadily for 40 years, interrupted in 2004 when high subsidies in Germany drastically increased demand there and greatly increased the price of purified silicon. The recession of 2008 and the onset of Chinese manufacturing caused prices to resume their decline. In the 4 years after January 2008, prices for solar modules in Germany dropped from a 3 to a 1 per peak watt. During that same time, production capacity surged with an annual growth of more than 50%. China increased market share from 8% in 2008 to over 55% in the last quarter of 2010. In December 2012, the price of Chinese solar panels had dropped to 60 cents per WP. Swanson's law is an observation similar to Moore's law that states that solar cell prices fall 20% for every doubling of industry capacity. It was featured in an article in the British weekly newspaper The Economist. Materials. Solar cell materials must have characteristics that match the spectrum of available light. Some cells are designed to handle sunlight that reaches the Earth's surface. Others are optimized for use in space. Light-absorbing materials can often be used in multiple physical configurations to take advantage of various absorption and charge separation mechanisms. Industrial cells are made of monocrystalline silicon, polycrystalline silicon, amorphous silicon, cadmium telluride, copper-indium selenide sulfide or GaAs-based multi-junction. As of 2014, typical solar cells are made from semiconductors wafers between 180 to 240 micrometers thick. Crystalline silicon. By far, the most prevalent bulk material for solar cells is crystalline silicon, also known as solar-grade silicon. Bulk silicon is separated into multiple categories according to crystallinity and crystal size and the resulting ingot, ribbon or wafer. These cells are entirely based around the concept of APN junction. Monocrystalline silicon are often made using the Czochralski process. Single crystal wafer cells tend to be expensive, and because they are cut from cylindrical ingots, do not completely cover a square solar cell module without a substantial waste of refined silicon. Hence most CC panels have uncovered gaps at their four corners. Polycrystalline silicon, or multicrystalline silicon, are made from cast square ingots large blocks of molten silicon carefully cooled and solidified. Poly-C cells are less expensive and less efficient than single monos. United States Department of Energy data show more polycrystalline than monocrystalline cells. Ribbon silicon is a type of polycrystalline silicon. It is formed by drawing flat thin films from molten silicon and results in a polycrystalline structure. These cells have lower efficiencies and costs than Poly-C due to a great reduction in silicon waste, as this approach does not require soaring from ingots. Mono-like multi-silicon. This form was developed in the 2000s and introduced commercially around 2009. Also called cast mono, Uses polycrystalline casting chambers with small seeds of mono material. The result is a bulk mono-like material that is polycrystalline around the outsides. When sliced for processing, the inner sections are high-efficiency mono-like cells, while the outer edges are sold as conventional poly. The result mono-like cells at poly-like prices. Thin film. Thin film technologies reduce the amount of active material in a cell. Most sandwich active material between two panes of glass. Since silicon solar panels only use one pane of glass, thin film panels are approximately twice as heavy as crystalline silicon panels, although they have a smaller ecological impact. The majority of film panels have 2 to 3 percentage points lower conversion efficiencies than crystalline silicon. Cadmium telluride, copper indium gallium selenide and amorphous silicon are three thin film technologies often used for outdoor applications. As of December 2013, CDTE cost per installed watt was 59 cents as reported by First Solar. CIGS technology laboratory demonstrations reached 20.4% as of December 2013. The lab efficiency of GaN as thin film technology topped 28%. The quantum efficiency of thin film solar cells is also lower due to reduced number of collected charge carriers per incident photon. Cadmium telluride. Cadmium telluride is the only thin film material so far to rival crystalline silicon in cost watt. However, cadmium is a highly toxic and tellurium supplies are limited. The cadmium present in the cells would be toxic if released. However, release is impossible during normal operation of the cells and is unlikely during IRES and residential roofs. A square meter of CDTE contains approximately the same amount of CD as a single C-cell nickel-cadmium battery, in a more stable and less soluble form. Copper indium gallium selenide. Copper indium gallium selenide is a direct band gap material. It has the highest efficiency among thin film materials. Traditional methods of fabrication involve vacuum processes including co-evaporation and sputtering. Recent developments at IBM and NanoSolar attempt to lower the cost by using non-vacuum solution processes. GaN as thin film cells. The Dutch Radboud University Nijmegen made a single-junction GaN cell that reached 25.8% in August 2008, using a 4 micrometer thick GaN layer transferred from a wafer-based to glass or plastic film. Recently, this increased to 28.8%. The efficiency was attributed to high-quality GaN epitaxial growth, surface passivation by the algas and the promotion of photon recycling. Silicon thin film. Silicon thin film cells are mainly deposited by chemical vapor deposition from silane gas and hydrogen gas. Depending on the deposition parameters, this can yield amorphous silicon, protocrystalline silicon or nanocrystalline silicon, also called microcrystalline silicon. Amorphous silicon is the most well-developed thin film technology to date. An amorphous silicon solar cell is made of amorphous or microcrystalline silicon. Amorphous silicon has a higher band gap than crystalline silicon, which means it absorbs the visible part of the solar spectrum more strongly than the higher energy infrared portion of the spectrum. The production of a C-thin film solar cells uses glass as a substrate and deposits a very thin layer of silicon by plasma-enhanced chemical vapor deposition. Protocrystalline silicon with a low volume fraction of nanocrystalline silicon is optimal for high open circuit voltage. NCC has about the same band gap as CC and NCC, and a C can advantageously be combined in thin layers, creating a layered cell called a tandem cell. The top cell in a C absorbs the visible light and leaves the infrared part of the spectrum for the bottom cell in NCC. Multi-junction cells. Multi-junction cells were originally developed for special applications such as satellites and space exploration, but are now used effectively with terrestrial solar concentrators. Multi-junction cells consist of multiple thin films, each essentially a solar cell in its own right, grown on top of each other, typically using metal-organic vapor phase epitaxy. A triple-junction cell, for example, may consist of the semiconductors, GaAs, GE, and GaN P2. Each layer has a different band gap energy to allow it to absorb electromagnetic radiation over a different portion of the spectrum. GaAs-based multi-junction devices are the most efficient solar cells to date. In October 15, 2012, triple-junction metamorphic cell reached a record high of 44%. Tandem solar cells based on monolithic, series-connected, gallium indium phosphide, gallium arsenide, and germanium pi-N junctions, are increasing sales, despite cost pressures. Between December 2006 and December 2007, the cost of 4N gallium metal rose from about $350 per kg to $680 per kg. Additionally, germanium metal prices have risen substantially to $1,000 a $1,200 per kg this year. Those materials include gallium, arsenic and germanium, pyrolytic boron nitride crucibles for growing crystals, and boron oxide. These products are critical to the entire substrate manufacturing industry. Triple-junction GaAs solar cells were used as the power source of the Dutch four-time World Solar Challenge winners Nuna in 2003, 2005 and 2007 and by the Dutch solar cars Solutra, 21 and 21 Revolution. Emerging research topics and pre-industrial technology in solar cells, light-absorbing dyes. Dye-sensitized solar cells are made of low-cost materials and do not need elaborate manufacturing equipment, so they can be made in a DIY fashion. In bulk it should be significantly less expensive than older solid-state cell designs. DSSCs can be engineered into flexible sheets and although its conversion efficiency is less than the best thin-film cells, its price-performance ratio may be high enough to allow them to compete with fossil fuel electrical generation. Typically a ruthenium metal organic dye is used as a monolayer of light-absorbing material. The dye-sensitized solar cell depends on a mesoporous layer of nanoparticulate titanium dioxide to greatly amplify the surface area, 200 a 300 m2 per gram TO2, as compared to approximately 10 m2 per gram of flat single crystal. The photogenerated electrons from the light-absorbing dye are passed on to the N-type TO2 and the holes are absorbed by an electrolyte on the other side of the dye. The circuit is completed by a redox couple in the electrolyte, which can be liquid or solid. This type of cell allows more flexible use of materials and is typically manufactured by screen printing or ultrasonic nozzles, with the potential for lower processing costs than those used for bulk solar cells. However, the dyes in these cells also suffer from degradation under heat and UV light and the cell casing is difficult to seal due to the solvents used in assembly. The first commercial shipment of DSSC solar modules occurred in July 2009 from G24i Innovations. Quantum dots. Quantum dot solar cells are based on the Gratzel cell, or dye-sensitized solar cell architecture, but employ low bandgap semiconductor nanoparticles, fabricated with crystallite sizes small enough to form quantum dots, such as CDS, CDSA, SB, 2S, 3, PBS, etc., instead of organic or organometallic dyes as light absorbers. QD's size quantization allows for the band gap to be tuned by simply changing particle size. They also have high extinction coefficients and have shown the possibility of multiple exciton generation. In a QDSC, a mesoporous layer of titanium dioxide nanoparticles forms the backbone of the cell, much like in a DSSC. This TO2 layer can then be made photoactive by coating with semiconductor quantum dots using chemical bath deposition, electrophoretic deposition or successive ionic layer adsorption and reaction. The electrical circuit is then completed through the use of a liquid or solid redox couple. The efficiency of QDSCs has increased to over 5% shown for both liquid junction and solid-state cells. In an effort to decrease production costs, the Prashant Kamat research group demonstrated a solar paint made with TO2 and CDSA that can be applied using a one-step method to any conductive surface with efficiencies over 1%. Organic polymer solar cells. Organic solar cells and polymer solar cells are built from thin films of organic semiconductors including polymers, such as polyvinylene vinylene and small molecule compounds like copper phthalocyanine and carbon fullerenes and fullerene derivatives such as PCBM. They can be processed from liquid solution, offering the possibility of a simple roll-to-roll printing process, potentially leading to inexpensive, large-scale production. In addition, these cells could be beneficial for some applications where mechanical flexibility and disposability are important. Current cell efficiencies are, however, very low, and practical devices are essentially non-existent. Energy conversion efficiencies achieved to date using conductive polymers are very low compared to inorganic materials. However, Konaka Power Plastic reached efficiency of 8.3% and organic tandem cells in 2012 reached 11.1%. The active region of an organic device consists of two materials, one electron donor and one electron acceptor. When a photon is converted into an electron-hole pair, typically in the donor material, the charges tend to remain bound in the form of an exciton, separating when the exciton diffuses to the donor-acceptor interface, unlike most other solar cell types. The short exciton diffusion lengths of most polymer systems tend to limit the efficiency of such devices. Nanostructured interfaces, sometimes in the form of bulk heterojunctions, can improve performance. In 2011, MIT and Michigan State researchers developed solar cells with a power efficiency close to 2% with a transparency to the human eye greater than 65%, achieved by selectively absorbing the ultraviolet and near-infrared parts of the spectrum with small molecule compounds. Researchers at UCLA more recently developed an analogous polymer solar cell, following the same approach, that is 70% transparent and has a 4% power conversion efficiency. These lightweight, flexible cells can be produced in bulk at a low cost and could be used to create power-generating windows. In 2013, researchers announced polymer cells with some 3% efficiency. They used block copolymers, self-assembling organic materials that arrange themselves into distinct layers. The research focused on P3HTBPFTBT that separates into bands some 16 nanometers wide. Manufacture. Solar cells share some of the same processing and manufacturing techniques as other semiconductor devices. However, the stringent requirements for cleanliness and quality control of semiconductor fabrication are more relaxed for solar cells, lowering costs. Polycrystalline silicon wafers are made by wire sawing block cast silicon ingots into 180 to 350 micrometer wafers. The wafers are usually lightly p-type doped. A surface diffusion of n-type dopants is performed on the front side of the wafer. This forms a pi-N junction a few hundred nanometers below the surface. Anti-reflection coatings are then typically applied to increase the amount of light coupled into the solar cell. Silicon nitride has gradually replaced titanium dioxide as the preferred material, because of its excellent surface passivation qualities. It prevents carrier recombination at the cell surface. A layer several hundred nanometers thick is applied using PECVD. Some solar cells have textured front surfaces that, like anti-reflection coatings, increase the amount of light reaching the wafer. Such surfaces were first applied to single-crystal silicon, followed by multicrystalline silicon somewhat later. A full-area metal contact is made on the back surface, and a grid-like metal contact made up of fine fingers, and larger bus bars are screen-printed onto the front surface using a silver paste. The rear contact is formed by screen-printing a metal paste, typically aluminium. Usually this contact covers the entire rear, though some designs employ a grid pattern. The paste is then fired at several hundred degrees Celsius to form metal electrodes in ohmic contact with the silicon. Some companies use an additional electroplating step to increase efficiency. After the metal contacts are made, the solar cells are interconnected by flat wires or metal ribbons, and assembled into modules or solar panels. Solar panels have a sheet of tempered glass on the front, and a polymer encapsulation on the back. Manufacturers and certification. National Renewable Energy Laboratory tests and validates solar technologies. 3 reliable groups certify solar equipment, UL and IEE and IEC. Solar cells are manufactured in volume in Japan, Germany, China, Taiwan, Malaysia and the United States, whereas Europe, China, the US, and Japan have dominated in installed systems. Other nations are requiring significant solar cell production capacity. Global PV cell module production increased by 10% in 2012 despite a 9% decline in solar energy investments according to the annual PV status report released by the European Commission's Joint Research Centre. Between 2009 and 2013 cell production has quadrupled. China, due to heavy government investment, China has become the dominant force in solar cell manufacturing. Chinese companies produced solar cells modules with a capacity of 23 GW in 2013. United States. Solar cell production in the U.S. has suffered due to the global financial crisis, but recovered partly due to the falling price of quality silicon. See also, references. Bibliography, Perlin, John. From Space to Earth, The Story of Solar Electricity. Earthscan. PA 50. ISBN A978-0-937948-14-9. External links, PV lighthouse calculators and resources for photovoltaic scientists and engineers, Photovoltaics CD-ROM online, solar cell manufacturing techniques, renewable energy, solar at DMOZ, Solar Energy Laboratory at University of Southampton, NASA's Photovoltaic Info, Green, M.A. Emery, K. Hishikawa, Y. Water, W. Solar Cell Efficiency Tables. Progress in Photovoltaics, Research and Applications 18, 346 doi, 10.1002/pip 1021. Electric energy from sun produced by light cell. Popular Mechanics, July 1931. Article on various 1930s research on solar cells.